He's gonna be good at watching you, so if you move, he will move with you.
Yeah. You're fine wherever. I mainly focus on that.
Yeah, I guess you can do whatever you want.
There's a pointer, just for a pointer, or laser, just you know. And it's kind of like
Okay, Pete.
we're good to go.
Hi, everyone. Welcome to one of our few colloquia in the last few weeks. I'm very happy to introduce today's speaker, Dr. Rich Neale. Dr. Neale comes to us from NCAR, National Center for Atmospheric Research, in the Climate and Global Dynamics section in AMP, Atmosphere and Model Processes. Yeah, that's not predictability. Wrong, Pete. So, Rich Neale got his PhD and his bachelor's in meteorology and physics at University of Reading. From there, he went and worked for a couple years at NOAA with Brian Mapes. And he has been at NCAR ever since, working on climate model development, atmospheric model development, and all sorts of things. He has 1.5 zillion papers that are super well cited, and he has tons of fun things to tell us about the CMIP 7 process and how the sausage is made for climate models. So take it away, Rich.
All right.
Green is good?
Green is good?
Yeah.
Okay, great.
Yep.
Thanks, Liz. Thank you so much. I really appreciate being invited. It's been a fun day so far, talking about everyone's research. A ton of great things going on. So for this talk, I thought, what's interesting to this group? And I thought, well, building models is probably unknown. Climate models, CMIP models. Please interrupt me if I use nomenclature people I'm not aware of. But basically, I hope to give you a little bit of insight into how NCAR in particular, of course, Community Earth System Model builds climate models, and as it relates to CMIP, IPCC, and essentially the way, the role that atmospheric processes play. So I just pretty much went through this basically, but briefly, yeah, my career, mostly in the UK to start off with, then NOAA. Some of the kind of topics that I've kind of plunged into, my PhD was aqua-planets, and quite nicely a project, kind of MIP-like project came from this of comparing lots of different models in aqua-planet mode, which is super insightful. It seems pretty boring, but actually when things like tropical wave variability that I know people are involved with here a lot, there's a lot of insight to be gained from the output of that. And then at NCAR, I've been involved research-wise. I'll do that in the next slide. So when I get a chance, what do? So I do ENSO type research, in particular ENSO surface coupling in the Pacific, and also its global impacts. Can we represent that in models? This will be very brief. Mount Juno oscillation, when I get a chance to do that also. Interested in what atmospheric processes in particular needed to simulate the MGO accurately. Convection, of course, goes without saying that that's important. And with other people, and I know Stephanie is involved with this, of course, can we represent the processes over the US? Blocking, very briefly, I've been involved with this in the past. And so, again, all from a modeling perspective, and in particular, how do these persistent circulation anomalies lead to these surface extremes? How will things change in the future? But to be honest, all this I've kind of viewed from the lens of, building a model, building the atmospheric version of the Community Earth System model. And my focus in terms of getting into the weeds has been deep convection. What are the important processes to get right? And of course, how can we improve aspects of the climate? In terms of CMIP and CESM models and IPCC, it all kind of rolled into one. So there's a big activity at NCAR and also in the university community to build the CESM. I focus on the atmosphere. CESM is a very well-established modeling system over many decades. We try to put the most cutting-edge science in the development. We've not tended to play it safe. That sometimes trips us up, but a lot of the time it results in a really a good model. It's broadly used. I heard, maybe not in AL6, but the previous one, AL5, CSM gave the largest contribution, either in simulation or data-wise, to the project, to the whole of the CMIP project. And again, just to emphasize, it's used by a broad cross-section of the research community across the US and across the world. The capabilities beyond CMIP are huge, large ensembles, decision makers, risk assessment. I just saw had a great discussion about downscaling CSM to look at Mississippi Delta outflow, and it's just a great use and a common use of CSM. But more recently, we're really pushing for the predictive weather type, I guess, requirements, and there's a lot of demand for that also. And again, just to reiterate, this decision-making piece. But basically, in short, the model had to be good to satisfy all or most of these requirements, and so the actual development process has to be really robust. And why? What do we use CMIP models for? This is, not unfamiliar to everyone. Is the IPCC type process. CSM is rolled into a lot of these models that are used to look at these evolution of air, global temperature, precipitation, sea ice, sea level change. And the key thing is, of all these models, of course, there's a large spread. So this the warming one here, SSP, 8.5 and 7, clearly there's a large spread. In temperature in particular, in precipitation, a huge spread. And it's negative to very positive by the end of the century, essentially. So this is just to illustrate that what happens in a model matters, and how, and by implication, how you develop a model really matters. And in terms of drilling down to those types of sensitivities, what I'm showing here is a table of, it's a little small, sorry for those in the back, but essentially a table of the types of feedback involved with future climate sensitivity. So different types of cloud feedback. The exact, it's not important at this point, but just to reiterate, all these feedbacks are important to how warm the climate gets, and implicitly the cloud changes, the precipitation changes, and there is varying degrees of confidence associated with these particular feedbacks, from high to low, but a lot of low confidence, and so you're building models in the presence of that kind of limited confidence, and so that those processes are really important as you build the model. You focus on those processes. There's another illustration of these feedbacks in response to, in this per degree C, so in response to a warming, these are the different feedbacks that occur. The red is CMIP 6, and the most recent assessment. The blue is CMIP 5 models, and the orange is CMIP 6 models. And essentially, there are a number of feedbacks associated, plant feedback, or water vapor feedback, there are a number of feedbacks that the system responds to temperature. But of course, not of course, but clearly the biggest uncertainty of the total net feedback here lies within how the clouds respond to surface temperature changes. So with that in mind, we know that cloud processes, somewhat, unsurprisingly, really are a focus of how we need to develop the model. So, taking a slight step back and how do you build a trusted model? People take a model, be it CSM versus GFDO model or other models. There are of order 30 models in the whole kind of archive of AR6, most recent IPCC. And it's how to build a trusted model. It is about trust as well. Why would you take one model above another of those from a set? Firstly, there's process. This has been opaque, I think people would say in the past. I just get this model and the data from these IPCC simulations, and many people may not care how that model comes into being or what the priorities are. But process is important, and expertise, I hope, and if that it comes from a center that provides this kind of expertise science-wise and has a track record, then you have more confidence. If it's fit for the purpose that you want these models to be used for, then you're more inclined to trust and use these models. And in a similar sense, what are the models targeting? It's relevant to climate change, etc. If you were targeting snow over northern Wisconsin as your main criteria, you wouldn't use it for global, tropical, or whatever climate problems. Performance, it has to be good. I mean, and develop it, knowing that you can't produce a model that has fantastic new representations of ice microphysics, but the performance is terrible. Robustness, CSM is an incredibly robust model. I did some quick calculation on the plane while I was being delayed 2 hours last night. And I think, when I say my interest in convection, I think the convection scheme is called nearly a quadrillion times in all the use of CSM, all the CMIP use over time. There are 48 time steps per day. And so, and it very rarely crashes. I'll show you one example where it did crash. But it was an extreme environment. But I think this is just an example, But I think the robustness of running a model is really important too. And then these two are more like utility, sensitivity. If you get, from my previous figures, if you get sensitivities that don't make sense, then no one is going to use the model. And it has to be, relevant. It has to be relevant, and it has to have utility in how it's used. Yeah, goes without saying. These are the two families of types of simulation from the most recent IPCC. And I just want to illustrate the expansiveness of the whole endeavor and how robust a model has to be. So in this pinky purple circle here, these really were the only kind of, requirements for simulations in CMIP 3, I believe, for the most part. So these are simple, AMIP, coupled, some future scenario type simulations. Now, AR6, if you look, move your eyes to both circles, and that's the requirements. Some of them are like requests, but CSM has met most of these requests, definitely on the projection side, so just emissions-driven type and boundary-driven type problems. But also, there's a lot more prediction based information in the report this time, and these are decadal predictions, hindcasts from particular starting periods, aspects of chemistry and regional air quality. And CSM2, I think, has met most of these. What's coming that's really making me sweat with the current development kind of activity is that instead of having simulation requirements based on specified burdens of things like CO2, nitrous oxide, etc., we really are pushing towards emission-driven representations of the climate into the future as well. So that's a hard challenge because we have predominantly been with these concentration-driven type activities. Now I mentioned that the quadrillion that never failed. Well, it did fail in the most extreme extension, which was out to 2300 at RCP 8.5, the very highest warming of, for the very longest distance. And the convection scheme failed, but it was mostly due to some iteration problem, which we fixed for the next quadrillion calculations. And of course, CSM again, I think kind of prides itself on the fact that it is an incredibly comprehensive modeling system, all available within kind of one entity. And it is, I'm sure you've seen this before, but it is quite amazing that the requirements that have been put on model building activities in recent decades. When the nascent, really kind of exciting period of the 60s, 70s, it was mostly atmospheric models, some simple land surface, maybe an ocean model. But then from the 80s and beyond, the complexity of sea ice, fully coupled, some chemistry, and then you see interactive vegetation, ice sheets, most recently, and yeah, we have capability for marine ecosystems as well in the current version of the model. Lots of version of the model has a very high top and significant resolution in the upper troposphere, upper stratosphere, and it enables us to do a lot of atmospheric chemistry that we have not been able to do before. But as well as the added complexity, here's the added constraint. Just one point here, that is, previous improvements cannot be lost. So during this kind of nascent period here, things would be improved rapidly, and there were had a lot of errors previous to that. But the problem is, and in my time, through the 2000s, we went from an El Nino that had a terrible period, like 3 years, high amplitude, but we made significant effort and made really good progress on having a much more realistic El Nino. But the problem is you have to maintain that. You have to maintain that from the perspective that it's hard to put out a model that had a good El Nino and then your next model does not. Of course you can, and if you can't recover a good El Nino, then so be it. But it is a kind of strange and implicit constraint that you cannot make aspects of the model that much worse. Okay. And is it a good model? I mean, this is CSM2, so the most recent assessment. You could put up a million of these at different metrics, but basically, these are a particular simple metric, root mean squared error based metric, I think, of aspects all the way down here. Sorry if you can't see it at the back, but flux-related quantities, precipitations. There's one on ENSO, some on kind of closed energetics. But essentially, if you move, reds here are the best, 97, 98, out of 100, and then yellows and greens and others. Good. But basically, CSM does, of all the 20, 30 models here, CSM, 3 ensemble members of the CSM2, for this, caveat, this particular metric, are the best in the whole set. So the model performs for these particular measures. And also, I think this is interesting, this kind of doubles down on CSM2 being a very broadly used model, so the expectations of a good model moving into the future are very high. Essentially, this is statistics of how the top 2 here, how the model has been downloaded since 2018 here, and then just in this year here. And then the bottom is essentially a metric of the user kind of input related to questions, etc., with CSM2. But essentially, in summary here, CSM2 has been downloaded 29,000 times. And even in 2024, it's around 1,500 unique downloads. So that's a lot of users. And so, just to reiterate, the expectation for a good model is high. Several tens of thousands of posts relating to the model and how it's used and asking questions to the community as well. Another point worth noting is that all or some components of CSM 1 and 2 are used by other modeling centers, or have been used as the nascent piece, the initial pieces of other modeling centers, in particular DOE, E3SM version, the NORISM Norwegian version is based on CAM5, and then this smaller Italian predictive model. So, and others, many others actually. And so, I just wanted to iterate this requirement of robustness in producing this version of the model, next version of the model. So, you ask yourself the question, are all CMIP models developed the same way? There's a few papers over the last 10 years or so that have kind of tried to reveal, crack open a bit of the mystery about how these models are produced. There are over 30 models in CMIP 6, and it's unlikely that the development priorities are the same. I know that CSM, we have a CMIP type development priority, but we also have our own development priorities. What does NCAR, what does the NCAR CSM community, what are they looking for in the model as well? And I think it's quite telling that one of these has the word art, and one has the word philosophy in the title. And that is kind of gives it away that there is, there's no law about how these things should be developed. In the way that CMIP has all these criteria, requirements, and very specific. This is how you do an AMIP simulation. Nowhere is it written that this is how you develop a model, which is kind of strange. It's very, in my experience, it's been a very hush-hush, implicit side conversation about what do you do with convection here, and what are you making the model do? And so it needs to be more formalized, there's no doubt. And this was an attempt in the last few years. In essence, it's hard to define one way of doing things, but this is predominantly about what CSM follows. Agreeing with observations, and particularly the observations we have most confidence in. And then you kind of tune, so you optimize the model and you calibrate the model best using unobserved parameters or very poorly observed parameters. In my own experience, entrainment is a parameter in the convection scheme. It's unobservable in essence on the scales that we're dealing with, around 100 kilometer grid scale. So you leverage that to provide the sensitivities you need. Some of the conclusion from these papers, increased transparency. And then the things that, the three kind of things that discern how different a model is developed is, do you develop it in a forcing period that is a pre-industrial, so a equilibrium climate, approximately equilibrium climate? Do you use the 20th century as a record to calibrate? Everyone would love to say no, but everyone does. And our initialized simulations used to calibrate. Maybe very recently, but prior to the last 2 or 3 years, probably not. So, when it comes to building the model, what's the key thing? Key thing is radiation. What do we want to know? What do we want to know in the future, in a gross sense, is how does radiation budget change in a future environment with a number of different forcing mechanisms and feedbacks? CO2, cloud, sensitivity, responsivity, etc. Because in the end, we know that around about now, or just prior to now, we have about 0.7 watts coming into the atmosphere, into the Earth system, more than in pre-industrial times. And even that, you can't see right here, but the estimate is 0.5 to 0.9. So even that, observationally, is not very well constrained. And of course, that's in the context of incoming flows of hundreds of watts, outgoing long-wave flows of hundreds of watts. And so, but we cannot have a coupled system that is 10 watts out of balance, either way. No matter how good the precipitation is, no matter how skillful the clouds look, or the temperature, wind distribution, our priority is to have a climate in 1850 that is zero imbalance, such that in the presence of 20th century changes in forcing mechanisms and feedback mechanisms, it's around 0.7, around a watt. And of course, you think, oh, that's easy. But then, then you start digging into what are the key processes that we have to focus on CSM, and I'm pretty sure most of the modeling centers focus on. And that is, clouds. Clouds, no surprise. Clouds, but not just clouds, how clouds, aerosol, and radiation primarily interact in the system. And, I'm not going to read all these out, but essentially, over the many decades, a number of processes that relate to how aerosols interact with clouds, how the particle sizes change in response to that, how the depth changes in response to that interaction, how the lifetime changes in response to the interaction. These are all key processes that we try and represent to the best of our abilities and to the limitations of the microphysics representations we put in, for example. So just keep in mind these sensitivities, aerosol, cloud, radiation, are key, and they're key to all those, and they're the most uncertain processes, but they're the most important to the radiation balances. and it's kind of even worse than that, because, the next thing you would like to do is get good distributions of precipitation, and with the aim of getting good predictions of precipitation in the future. And I've just, again, thrown in an IPCC figure here, which is essentially, the precipitation change mid-century, wintertime, and summertime. And this is in the color. In the colors, it's a change in precipitation, so blues are wet and reds are dry. But the hashed areas, essentially where low model agreement is, where they don't agree. I think less than 80% of the models, are in agreement. And so that's nearly everywhere. It's nearly everywhere on the globe, which is really disappointing. And, to a certain extent, I've kind of thrown this on here because it really represents the complexity of precipitation and microphysics and how that's involved in water cycles. It's not simply a case of clouds form, condensation, precipitation, below zero. There's a lot, I know you guys know this, but there's so much complexity involved in the particle types, the particle distributions within the cloud, and how they respond to, a warmer climate, more extreme rainfall. It's all in here, and, we really focus really hard on the microphysical representations in the model because, these have been clearly demonstrated to be all super important. Something like, there's a grapple, if people are not familiar with that content. It's like kind of an ice type particle, and it's super important in deep convective regions. And it's something we're just considering now because we know it is super important. Going too slow. So, in terms of CSM, this is the guts of what we do. Okay, if you take nothing else from this model and think about how do you develop a model, this is what NCAR and the university community does in terms of going from A to B. A is like ideas almost of what we should be putting in models, and Z is like CSM3, the next version of the model. So what tends to happen is, people, scientists, researchers develop theory, process studies related to processes they think, are missing in the models or could be represented better in the models. That tends to be an offline development away from the main development activity. And if you feel inclined to take part in this, I encourage you to, kind of, like I say, take part in the whole community to try and have an impact. It's great. And the next step is kind of a collaborative development, and that occurs between NCAR staff or community researchers. And we have a number of these working groups. I was head of the atmospheric working group a few years back, and so then you would move to kind of a mature development that you think your scheme that you have, you've developed it, to maturity, and it's ready to be considered for inclusion in a future model version. So this vetting goes on by this working group, and that's followed by more in-depth atmospheric development. So the model, you include it in the atmospheric component of the model. It becomes part of the CSM development workflow, and there are a number of kind of requirements for that to be kind of become robust, be compatible with other changes. And at that point, you jump onto the whole system development. This is where we are right now in the next cycle. So essentially, we've brought together what we think are our best changes, best improvements to different components: land, sea ice, land ice, ocean, atmosphere. And so we're in this iterative kind of workflow right now where we're running a number of fully coupled simulations, many decades long each time. And so we're looking for surprises. You just never know until you fully couple models. Energy balance, like I say, that is numero uno, that has to be satisfied. And then there's kind of a tiered list of metrics and comparisons that need to be made to make sure we're producing a more skillful model. And there are more than these things, but I would say these are the top few that we would look at as a priority. And then we would make changes and we'd go through the whole process again. It's very laborious work, and it's not very well assisted by statistical methods, machine learning, emulators, etc. So that is changing. And then finally, you go through broader configurations that need to be shown to perform with your changes. Like I said, chemistry and high top. And then additional scenarios. So then we're looking at our 20th century type simulations. And what is the climate sensitivity, etc. And then you're in the production time. These are the simulations that go into the next phase of the IPCC assessment CMIP. So that was just my putting down on paper what we actually do during model development. A little dry, but I think it's illustrative. So in terms of going from CSM1, which is CAM 5 atmosphere, to CSM2, which is CAM 6 atmosphere. This is my schematic of what was included here, and I wanted to kind of give you a sense of what we changed, but I think it's too much information. But I would basically note from here, there's a lot of individual isolated schemes in some way. A microphysics scheme, cloud macrophysics, a boundary layer, shallow convection and deep convection. And the model performed quite well. But our philosophy was to be more consistent, was to go to something more holistic that was related to moist turbulence. So I'll flick it back and forth here, individual schemes here, and then now we have, I'm not going to go into detail about this at all, but a scheme that is called cloud layers unified by binormals. And essentially, the essence I want you to take away is this is now moist turbulence. Before we had shallow cumulus boundary layer scheme, etc. Now we're more consistent, we believe, including these schemes that are more mutually consistent because they're all part of a moist turbulence, high order turbulence scheme. So I just wanted to give you the takeaway there. And in terms of the landscape of how we've been changing over the years, I did this work a few years ago, and I thought it was always, I think it's interesting to see where you've been and how the model performs. And so, left to right is time, 1998 here to present, well, next year. And these are different versions of the atmosphere model, and then in red, and then the coupled model. And, over time, these are the schemes that have been included. I won't go into details here, but everything on the physics side, the vertical levels, resolution, etc. And I just want to emphasize that, earlier on in the period, I guess, prior to 2010, we were pretty conservative about putting new things in, changing things, improving things. But there's no doubt from 2011 on that we've not been as conservative. And all these greens are changes each time. So before we were changing particular representations of processes each time. Now we've been pretty aggressive, and that's good and bad. As you can imagine, it takes a lot to understand a model that's changing a lot. What's happened over that time? I think this is pretty illustrative of, have we improved? I mean, that's a simple question, I guess. And so we're looking at, in this case, just the atmosphere models for an annual mean AMIT metric for all these variables: precip, temperature, cloud forcings, etc. And in this case, it's just a CAM 6 now. From red to green, red is the worst. In each row, red is the worst score, the worst Rudy squared error. Green is the best. And so if it's this one is red and that one is green, you've improved from beginning to end. You've improved, and that is largely the case. There are some, CAM 6 was not as good in temperature as CAM 4. Precipitation is pretty across the board was better. One thing that wasn't better was long wave cloud forcing, and the best we had was 25 years ago by this metric. There's a reason. Well, there's a reason potentially for that. So I thought it was interesting to say, how have we improved, and are we improving now? So this is just to kind of reiterate what happened from 1982. This is one of the first models that NCAR put together, and these are the bias is around 2 of precipitation. CAM6, which is CSM2, is now 0.87. And it's hard to say whether that's amazingly better or better, but it is quite a bit better. And the question is, where are we now, right now, in the last month with CAM7? Oh, just to reiterate, this was just an atmosphere model. This is everything model. We had to do all these things with this model as well. And where are we right now with CAM7, annual biases? And you're like, at this point in the cycle, it's like, well, yeah, it's, 0.87, now we're above 1. The patterns look quite similar. We are working on a couple of things here, which is a little small here. In summertime, we have this great red spot, which is this spurious monsoon extension into the Pacific. And we're also having, it's more general than just over the Himalayas, but we're having excessive precip over orography issues. And so that's a good example of something we can try and address, and we've identified it as a problem. For that, as I mentioned before, for that long wave cloud forcing issue, so here was the best, the earliest one, just 7.54, and then, out to like CAM5, it's 10. Now the issue is, a lot of the properties required for the ice particles in upper tropospheric cloud, which are key for long-wave cloud forcing throughout the globe, were specified because we did not have predictive hydromedia types, and we do now in CAM6. So that's much harder to represent, but we're still not doing as well by this particular metric as we were many years ago. So complexity adds more difficulty sometimes in terms of getting the right answer. Just throw this one in there because it's MGO related, but how have we done in terms of developing the model over the years for the MGO? And this is just the power associated with the wavelength frequency windowing for the MGO. And this trend, but over the years we've improved the variance associated with this. I've worked on this associated with improving humidity, sensitivity, and convection. Many other centers did very similar things. So this is a good example of kind of copying or collaboration with other centers to know that this was an important process. And this is where we are fully coupled in CSM2. So we're doing a pretty good job. All right, doing too slow. I thought I'd show a couple of challenging examples now of developing a model. Things going awry and trying to fix them, or like just not really understanding what's happening. One of the coupling problems that is absolutely like bedeviled CSM in the last 5, 6, 7 years is that an issue of Labrador sea ice freezing. So Labrador sea ice in this region here, well, the Labrador Sea here does not freeze for the most part. It stays ice-free. And I'll show in a second that that was not the case in recent versions of CSM2, which we've been fighting with, and CSM3 actually. But the interesting thing from my point of view is that this is the most fascinating couple problem on the globe, observationally and modeling, I think, because you have very complex ocean currents around the boundaries of those topographic features, the East Labrador, West Labrador currents. You have sea ice that does encroach there to some extent. From the atmospheric perspective, you have these like cold air outbreaks where you get some of the largest sensible heat fluxes on the planet here as the air comes up of Canada. The cold air comes out and over warmer SSTs. You're having really localized, but some of the deepest ocean convection down to 1 kilometer or 2 in this region, and this successively happens every year. So just to emphasize, this is a big kind of like nexus of strong processes that have to be coupled in the world. And so the problem that we had was here, it's just for this region here, it's repeated up here, is the Labrador sea ice extent in wintertime. And so this is an observational product here, having SST. The previous version for CMIP 5 was not a problem. And then in developing CSM2, really a lot of sea ice was like spilling out into the North Atlantic, killing off, it's kind of chicken or egg. At the same time, deep convection in the ocean was being shut off. And so that was part of the problem, was to determine what was forming what, and whether another thing I forgot to mention, sorry, is like meltwater from Greenland. Obviously, it impacts freshwater input into the buoyancy into the upper ocean. Other models actually have had a similar problem, E3SM, but that is based on CSM. So, and we fixed it by luck, to be honest. And it's a little complicated here, but basically, we would run a number of ensemble members. Some would freeze over. These are the purple ones that go over here to ice fraction. Some would continue. And we chose one of these that continued and did not freeze over to be the basis of our CMIP model. Now, you could say that, like, well, you should have understood it and prevented that from happening. We did. We just put a lot of work into it. And it was very difficult to understand. But I would say that, like, are we dealing with a system that is actually close to this state shift? So those oceanographers know this probably, but like observed over the 20th century, there has been, a tendency, particularly in the last 10, 15 years, for a slowdown. The black, you can't quite see it, but essentially slowing down of the AMOC here, and this associated with that northern region, cooling of SSTs, blues, and then it's kind of further US South region warming. So many of the developers made an argument that, like, it is on a knife edge of, instability of, like, tipping. And it's just that we've tipped maybe 100 years too early, which of course in that, in like paleo timescales is nothing. But it's hard to give a model that's meant to represent present day that is frozen over the Labrador Sea. So it was a bit of a dilemma. We did, like I say, we're able to choose this version of the model that did not freeze, and it's unsatisfying, but it's what we had to do.
Why didn't it freeze?
Why didn't it freeze?
Yeah.
It was just, I think it was just some stochastic. We started the simulations from a slightly earlier point and subjected it to the atmosphere, a different atmosphere, and then over a series of like 3 decades, it avoided the freeze.
Can I ask another question?
Yeah.
What was different about the atmosphere?
Well,
I mean, if you had to sum it up.
I don't know, and I think it's just a stochastic thing. I don't think.
Really?
Yeah, I do. I think it's an integrated, because the atmosphere diverges, it's on top of a different ocean. The actual stochasticity of the atmosphere moving forward. One time it led to a freeze, and another time it managed to avoid it. So it's not the state per se; it's the fact that the resulting, stochastic of the atmosphere, but also longer timescales must be coupling with different.
Yeah, modified ocean modifies the atmosphere.
Yeah,
and so
exactly.
on.
Yeah,
Okay.
yeah. I can't pretend that we spent a lot of people smarter than me spent a lot of time on it. It was really challenging. The second one, which is super interesting, and in some ways more dramatic, forcing data sets. So when we got to the period where, right, we like our model now, we want to run 20th century simulations, just to test and maybe make small changes over that time period. And so, this is where, 125 is in the folklore of being a really good model. But we had, over the 20th century, you could argue it's a little cool going into the 80s, but that's fine. We thought we could work with this. And then the next step that came was like, CMIP has provided us with new data sets. The observationalists have a lot more faith in the emissions, aerosols in particular, the regional distribution. And so we said, let's just introduce these and we'll keep moving forward. And of course, what happened is we introduced these data sets, and there was, cooling in the 20th century, which again is a big no-no for a model. And many models suffered with this problem. And so we went in, we tried to understand, we knew it was a aerosol indirect effect problem. So the aerosol that was resulting from these new emissions were impacting low cloud properties too severely, lightening them too much, so cooling the system in the mid to late 20th century. And we worked very hard, not important that the individual simulations, but important that we managed to recover the 20th century 20th century evolution much more skillfully. And this is the kind of philosophical dilemma here is a little bit is, if you have a good model, it should reproduce the 20th century when subject to the correct forces. And it didn't. And we modified the formulation of the model to do this. And there are arguments saying you should not do that. But we kind of had no choice that we were up against the wall on this one. And you can see it kind of here in terms of, this is just the shortwave cloud forcing difference when you subject to a version of the model that has pre-industrial aerosols and a version of the model that has the new 20th century aerosols. And you can see that these big areas of cooling associated with low cloud, stratocumulus cloud. And there's a big region here, and this is fascinating because what happened is they introduced some enormous emissions from an aluminum smelter on the Chilean coast, I think, or Peruvian coast. And this had the impact where it was added to the column of just like brightening the clouds like crazy. And so the protocol for these emissions was nothing about how you distribute it in the vertical, and just small changes in how this smelter distributed these aerosols in the vertical made a huge impact in improving this. So, I don't know, it's kind of sketchy. but that's what we had to deal with. I mean, yeah, that's the challenge is you do get a lot of these external factors that you have to deal with and that are really challenging. I'm going extremely slowly, but I think this is super interesting, I think. So, one of the things that CSM2 is known for, amongst a few other models, is a high climate sensitivity. So essentially, if you, in the framework that you calculate climate sensitivity, if you subject CSM2 to a doubling of CO2, you'll increase the surface temperature by about nearly close to 6 Kelvin, as you can see here. So, ignore this bottom one for a second. The equilibrium climate sensitivity is here. But essentially, because the typical value is known as Sherwood value here is 2.5 to 4 is known as typical value. And we thought at the time, well, it is what it is. We have a different model. We made all these big changes, and it just, there's nothing inherently wrong to our knowledge with it. And so we've got obviously all the CMIP simulations with this, and we did a number of different tests, typical tests, and it never really showed up as a kind of problematic thing. Until this paper here by Jan Zhu, a paleo-climate specialist, was reconfiguring the model to run in a last glacial maximum, which of course is cooling. So the approximate estimate here is around whatever 6 Kelvin for that time period. But when he introduced CSM2 to that forcing framework, it just went off the rails. Cool. The sensitivity was huge. And so, as I've shown in the next slide, he demonstrated that by changing certain aspects of the microphysics, just seemingly small aspects, we were able to recover something that was much more realistic in terms of the proximate. This is a good alternative test for models is paleo-climate, and we missed it because we didn't do it during the development process. And as it turns out, with these changes, returned this climate sensitivity back to close to CSM1 around 4. So I think I'm gonna skip it. But basically, it was something to do. No, it was a specific thing to do with the ice microphysics that with some limiter. Microphysics has lots of limiters in there because they're very fast processes. They get out of hand on these long time steps. But essentially, a very small change we did not pick up in our development process led to this. And so we now have this like paleo-calibrated version of the problem which has that fixed in. It doesn't make that much difference for kind of low forcing scenarios, 20th century, immediate future out to 2100, doesn't make much difference. But for these strong forcing scenarios, it does. So now I'm going to skip that. And I'll just end with a couple of different methods. There was my boxes of development pathways, etc. And of course, it's brute force. There's no two ways about it. We've kind of dreamed of a way that we could do this in a less brute force way of running long, expensive simulations. But now there are ways to do this. One way is that would help us select parameters, for example, and use what's called perturb physics ensembles. So essentially, you take usually quite short simulations, maybe a year, 2, 3, of multiple simulations where we perturb the key parameters, entrainment, for example, or aspects of the microphysics, or many other mostly unobservable parameters. And then you sample the model to say, how does it occupy this multi-dimensional space that you've given it by perturbing all these parameters in a controlled setting. And so, one thing that it gives you, for example, this is, it gives you a sense of the variability of, in this case, long-wave cloud forcing, so the radiative forcing predominantly of the tropospheric clouds. And it gives you bounds on of the variations based on all those perturbations. You can view this as, showing you what the range is and enabling you to select parameters that, from that range, could give rise to a better simulation when you put it in the standard model. There are all caveats to this in that even though you could find a set of parameters which give the correct mean, that does not necessarily mean, here we go, back to the energy imbalance. This is a histogram of all the different simulations and the energy imbalance that gives you. And so the best simulation here in terms of mapping to the observations could give you wildly different energy imbalances, which of course won't fly because you put that in a climate model and it'll cool by 10 watts per meter squared, so that's not doable. But what it does do quite nicely is it can tell you what are the expansiveness of the feedbacks, for example. And here the yellow, this is like the individual, a broad breakdown of feedback. So shortwave cloud feedback, which tends to be low clouds, high clouds, and then the total feedback. Yellow is the numbers that came from CMIP 6, so the very first plot, one of the first plots actually. And this is from this perturbed physics ensemble in CSM 2. And it shows you, it's very informative to know that the expansiveness of a lot of these feedbacks, which we said was key to the climate sensitivity, climate feedbacks into the future, covers very much similar terrain as the whole range of the CMIP models for all these feedbacks. And so it really does, it enables you to learn more about the model and the variability, but also be able to understand that the parameters that you pick, what are the feedbacks, for example, that would result from that. I'm going to skip that, and this is my last slide. And so, one thing, of course, someone mentioned is, I think, Jack was mentioning machine learning, and I think it's taking off now, and there's no doubt that next cycle will be cycle development, however it looks, may not look traditional CMIP, may look very different. How that evolves, excuse me, will involve machine learning. Now, the nature of that is unclear. There's a couple of projects NCAR is pretty involved with, which is this NSF LEAP project, and then this is the Google Schmidt Futures, got it in 2 lines. But essentially, it's doing the machine learning legwork, figuring out what types of neural nets and machine learning type approaches can provide, for example, learning capabilities that could replace a parameterization We have one where we replaced the warm rain parameterization, a very specific part of the microphysics, with a machine learning based parameterization. And you know, these things, and it's hard to know exactly what the use of the particular implementations of this, but of course everyone knows it's faster, and you know, if you're trying to understand certain aspects of the sensitivity of the model but don't care about others, but you want an accurate representation of that, then one could imagine that you replace those pieces in the model. So that's kind of happening now and will be mature, I think, in 3 or 4 years' time. So that's it. Building a model is daunting, I guess, with an ever-increasing list of requirements. How model, you know, fidelity translate to CMIP, kind of like aspect performance reality coupling is not clear. And they didn't talk about it. Emergent constraints may have are helping with that. The killer processes, you know, clouds and feedbacks and how they relate to aerosol and radiation interactions. And unfortunately, these are the types of processes where the uncertainty is very low, or getting better, but still quite low. Yeah, one CMIP model to rule them all will no longer be the case moving forward. And I didn't talk about it at all, but we're investing in multiple approaches as it relates to regional modeling, high resolution, et cetera, and you know, prediction, et cetera. So it'll be more diffuse than it is even now. My voice is going, we'll stop. Thanks.
Let's get a student question first. Yeah.
Yeah, I'll start with an easy one. So you showed a lot of metrics. Like there was that one plot that you had that had like grids. There was like the good scores are in red, the bad scores are like more in green. Just how is that metric qualified or like calculated? I guess.
You know, I think it's in relation to the other models.
Okay.
I think, yeah. There's been a couple of iterations on that. Scientist called John Vasula developed that, and I know he's had a number of iterations. But that particular one, I think it's in relation to the other models, like maybe at the 90th percentile of the models, I think. But I could definitely find, there's a good paper on that too.
Hamish.
Yeah, you mentioned a few times about prioritizing different things. Like start with energy and then go temperature and then go a few things up there. Who decides at the end of the day what you should be working on? Is it like a council of CESM to be like, you should be doing these 3 things and prioritize energy first? Or?
Yeah. Definitely energy. I think there's no disagreement with something like energy. You know, I hate to say this, and it's personality driven to a certain extent. You know, when I came in, you know, tropical meteorologist with an interest in convection, MGO, and ENSO, and I looked into it, and I figured out I could make improvements, and then, you know, but I looked into it more and more and more, and it shouldn't be like that. I totally agree. But I think the ones that I showed are hard to disagree with, I think, in terms of importance. But what comes next, I think, can be quite personality driven. You have someone who comes in who's an expert in some particular, you know, not wildlife is a bad example, but like an expert in land-atmosphere interactions. Then you get that experience, and you get the metrics, the diagnostic. That's another big thing. Someone comes in with really great metrics about how to look at the model, that's a winner. I mean, it's hard to turn it down. But ideally, yeah, we should have more. We should have sit around and come to a more objective understanding of what's important. But I think it's hard to know. And I know other models. I know the Met Office, for example, they have a very hard list of what the top performance metrics are. I don't know what they are, but like, you know, and they stick to it, and you are working on that, and you work. So I don't know whether that's more successful or more kind of organic. Very long answer.
Tracy.
Thanks for your talk very much. I was wondering, just sort of to build on that, if you could comment on what issues face CESM as a community model versus some of these lab-based models like GFDL or other ones that are not community models, and kind of the pros and cons of that.
Yeah, that's a great question. So CSM, I think, probably prides itself, and WARF being like probably one of the first community models, community developed as well as community like distributed as well. You know, in terms of documentation and tutorials and work really hard, still working really hard on that. You know, it's such resources, there's no doubt about it. You know, there are people dedicated to providing those types of capability. I mean, I'll do the funding whine right now. I didn't say, but like, you know, for CMIP 3 through the CMIP 6, we have no more people working on the model than we did then. And, you know, I'll show you, there's all those, the capabilities have just exploded. But everyone, I think people see the benefits. I mean, the places you mentioned, you know, UFS, E3SM, for example, we never really wanted to be a community model, but they are now, they have community. UFS really is pushing hard for the, you know, whole modeling activity to be community-based. Even GFDL, I think, as well, are pushing. So it's recognized as being important, but it's definitely diluted our pool of scientists who would come and work on CSM, particularly E3SM. There's a lot of, you know, NSF people. NSF does not really fund model development beyond NCOM. But E3SM has university programs to fund developers outside DO. And, you know, just hard math. A lot of people that, you know, did a lot of work for us now do work for E3SM. It's not as if, you know, it's not quite as brutal as that, but they have to pay the bills.
I think there's a hand back first. Sure, Evan. Yeah, you have.
Okay. So you mentioned it right at the end here about the high resolution model not being another kind of dimension of where we're going forward. Do you have any sense for the relative importance of increasing the complexity of these parameterization schemes and for using machine learning to help develop them versus just making the model higher resolution and the benefits that come from that?
That's a great question. I mean, we have, you know, high resolutions are dilemma. I can't remember speaking to, but like, we can produce an amazing model, but you just won't be able to run it. I mean, that is often our like premises. We can produce probably a 6 kilometer global model, but you just can't run it. I mean, and so the kind of compromise that we're pushing more than anything is it's called a regional refinement. So you have a global model, but most of it is really coarse. But then you're able to telescope down. It's like regional modeling, but it's on a global domain, and that's proving really successful and popular with people using that over, you know, tropical cyclones, atmospheric rivers, MGO, you know, and you just like, you know, focus on the region you think is important. Now, if the whole globe is about always this amazing interactive modal interaction, then you're missing something if you have very low resolution elsewhere. But I think for a lot of problems, and in particular as it relates to, you know, people, decision makers and stuff, I mean, it really is the way that we will go, I think. We're not going to produce NCAR, it's not going to produce a very high resolution climate model to be run in these ways, to run in CMIP ways. Yes.
Yeah, thanks, Rich. Great talk. And thank you also for sticking with this ugly problem. I mean, all of you. Really, it's an astonishingly unrelenting set of setbacks. But you keep on going and you keep on making things better. It's amazing. I had a question about the use of machine learning, and I ask it from a very naive perspective. The idea might be, there might be two broad universes. One in which you take a parameterization, put it on the operating table, and figure out with the tools that machine learning allow how to optimize that parameterization. The other might be, take the ecosystem of parameterizations that compose your model and figure out with machine learning tools how that ecosystem works best.
Right.
Which one do you think would be more fruitful?
I think the individual kind of approach that you said to start off with, I think, because you know, I kind of feel the second is almost irreducible. It's just such a hard problem, I think, to understand.
You don't want to understand it. You want the machine to understand it.
Yeah.
So to
Interpret,
optimize how
I
it
guess,
works, right?
interpret.
Yeah.
And I guess that, what would you do that information then, I guess, is the question also.
I guess that's really right. I mean, it comes up against the goals that you have, right?
Right,
Which you've
right.
stated really eloquently today. So, yeah, I want to know what your opinion was. I guess.
No, yeah, I know, yeah. And you know, I think it kind of needs leadership right now in the machine learning. I mean, those two efforts, yeah, I understand, are great, but I think I don't know, it's one of these things, and maybe it's fine, there's no leaching, it's just like bubbling up, and it does feel a little bit like that. But at, you know, at one end, you know, you can run the European, you know, center model forecast in like 50 seconds for a 10-day forecast. And do we want that? Is that useful for us to run the model in 50 seconds that is completely machine learned from all the parameterizations? I don't know. I mean,
Yeah,
as a
not for me.
as a physical scientist, it kind of makes me weep a little bit.
Yeah, I agree with that. I agree.
I'm like, you know, machine learning is amazing. I mean, it's amazing what you can do, but like, you know, being a physical scientist, I'm like, do I understand the process?
Right. Yeah, I
Yeah,
agree with
I
that.
don't know. Yeah, answer the question.
Any more questions? And why don't we thank Rich again?